Chemical properties of benzene and its derivatives. Electrophilic aromatic substitution on benzene can be classified into halogenation, nitration, FRIEDEL-CRAFTS alkylation, and FRIEDEL-CRAFTS acylation. There are two reactions of alkyl benzene, which are oxidation with hot acidified KMnO4 or K2Cr2O7, and halogenation, which is free radical substitution. Electrophilic aromatic substitution, a type of reaction for aromatic ring. Benzene does not undergo addition reaction. Instead, it undergoes the substitution due to its stable pi electron system. Benzene is electron-rich species, so it reacts with electrophile. Hydrogen atom is replaced by electrophile, any electrophile. It will replace this hydrogen atom and the product will be substituted benzene and H+. General mechanism of electrophilic aromatic substitution. Step number 1, addition of electrophile to the benzene ring, making the carbon and electrophile atom bond. This reaction is slow, so this double bond, the carbon-carbon double bond, 2 electrons of one bond are used to form bond with the electrophile. So when the bond is used, this carbon, one carbon involved in bonding with the E, another carbon is not bonding with any atom, just bonded to hydrogen, and it is not octet, so it becomes arenium ion. Here this carbon positive, overall it becomes arenium ion. And when this carbon is positive, the double bond here will be change its position to here to make this carbon stable again, not positive. But when this double bond change its position, this carbon here becomes positive, and the double bond near to this carbon change its position to make this carbon stable again. And finally, this carbon becomes positive, and the hydrogen on the arenium ion will be attacked with a nucleophile. It will attack means it will use its lone pair electron to form bond with this hydrogen, and then these 2 electrons sharing will be used to stabilize this positively charged carbon, making the double bond again and making this arenium ion have 3 double bond again. So step number 2 is proton transfer and restoring the aromaticity of the aromatic ring. Halogenation. The reactants are benzene and halogens. Halogens used are chlorine or bromine. Iodine is not used because it is unreactive. Fluorine will not be used because it is too violent. The condition for this halogenation of aromatic compound is Lewis acid such as FeCl3 or FeBr3. For example, here, aromatic compound reacts with bromine in the presence of catalyst FeBr3. One Br atom from this bromine replace or substitute the hydrogen atom, one hydrogen atom here, and that hydrogen atom will form bond with another bromine atom from Br2 as the side product. So the product will be bromobenzene and HBr. The mechanism of this process, or the mechanism of the halogenation, start with step 1, formation of complex ion. This is needed because this Lewis acid is needed to increase the polarity between polar molecule, because this Br and Br have the same electronegativity, so it cannot break by its own. the bond cannot break by its own. So in order for this Br to form Br plus, this FeBr3, the catalyst, is required to increase the polarity of this Br2 to form complex that makes halogen molecule more electrophilic. Because we know that our aromatic compound is nucleophile, the electrophile is Br. So because this aromatic compound is electron rich, so this is nucleophile. To make this Br2 electrophile, it needs to have electrophilic site. Since both Br2 atoms are the same electronegativity, so it cannot make electrophilic site by its own. So that's why the catalyst FeBr3 is used. How the catalyst FeBr3 make this Br2 become electrophile? This Br atom, one of the Br atom, use its lone pair of electron to form bond with Fe, because we know that FeBr3, this Fe is incomplete octet. So this is the electrophilic site. When these two react, this Br here becomes nucleophilic site. Okay, this Br here becomes nucleophilic site, here electrophilic site. This Br use one of its lone pair electrons to form bond with Fe and making this complex FeBr3. This Fe become minus because it has 8 electrons in total. And then since this Br lose one of its lone pair electron, this Br become Br positive. So it needs to gain its lone pair again. By breaking this bond, it uses this sharing electron, 2 electrons of this bond are used to transfer to this Br plus. Transfer to this Br plus, making this FeBr4 minus, and this Br becomes Br positive because it only has 6 electrons now. So now we have the electrophilic Br. Now our aromatic compound can attack this Br plus. That's the function of the catalyst FeBr3, to increase polarity of halogen molecule to make this Br electrophile. Now this Br is electrophile. Then we can proceed with step number 2, formation of aranium ion. Now our Br plus electrophile, the nucleophilic aromatic ring use its double bond to form bond with the Br plus. So it form bond with Br plus, one of the carbon, because the double bond involve 2 carbons. When it form bond with Br, only one carbon form bond with Br. Another carbon becomes positively charged. So since this carbon is used to form bond with Br, the carbon up here becomes positively charged. This is not stable, positively charged carbon. So it will take 2 electrons from the double bond to stabilize it. So change its position, these 2 electrons change position to here to make this carbon stable again. And when it changes its position, now the carbon is stable, but the problem now, this carbon over here is positively charged because it moves its double bond. This carbon here, it's stable because it still has the double bond, but the carbon over here becomes positively charged. So it takes the double bond from the nearest carbon, so which is this double bond, is used to change the position here to make this carbon stable again. So this carbon becomes stable, this carbon becomes stable. Now the new problem is this carbon, it becomes positively charged. The pi electron of aromatic benzene ring acts as a nucleophile, attacking the complex ion. This step forms aranium ion as an intermediate, so this is aranium ion. Step number 3 is loss of a proton in the form of H+. So FeBr4- from step 1 is used to get the proton. Here we know that Fe-, because Fe prefer to have 3 bonds only, it is stable as incomplete octet. So it removes one of the bromine atom by giving this 2 sharing electron to this bromine atom, making this bromine atom to have 8 electron in total, Br-, and 2 of the electrons from bromine, 2 electrons from bromine here is used to form bond with the hydrogen over here, and the 2 electron from the CH bond is used to be transferred to this carbon, making the double bond again. So this is the product. A proton is removed from the aranium ion to form the products and regenerate. The FeBr3 catalyst is regenerate and can be used in step 1 again. And this is the side product HBr. Comes from this proton, reacts with this Br, form bonds with this Br. So this is the side product HBr. Main product bromobenzene. Catalyst is regenerate again to be used in step number 1. Next, nitration reaction. Reactants are benzene and concentrated HNO3. The conditions are concentrated sulfuric acid, and the temperature must be between 50 to 55 degrees Celsius. Make sure the reactants is concentrated HNO3 and the condition concentrated sulfuric acid. Then nitrobenzene can be formed with the side product water. The mechanism of nitration start with step number 1, formation of nitronium ion. So nitronium ion is NO2+. We have HNO3. Have HNO3, concentrated HNO3, to be reacted with the benzene ring. But in order for the benzene ring here to attack the NO2, to attack the NO, we must make this HNO3 electrophile first. So to make this HNO3 electrophile, by reacting it with the H2SO4, the oxygen in HNO3 use one of its lone pair to form bond with the hydrogen in sulfuric acid, H2SO4. And in order for this oxygen to form bond with hydrogen, the bonding electron here must be transferred back to the oxygen of sulfuric acid, making H2NO3. H2NO3. Okay, H2NO3. Now this oxygen is positively charged because it used one of its lone pair electron to form bond with the hydrogen. And the sulfuric acid becomes HSO4- because it loses one of the hydrogen and becomes HSO4-. This oxygen over here does not prefer to be positively charged. So what it does is, this bonding between O and NO2, the electrons bonding, both 2 electrons are used to be transferred back to the oxygen here, forming water molecule and NO2 plus nitronium ion. Now NO2 plus is the electrophile. Now benzene ring is ready to attack the nitronium ion. So this benzene ring, formation of aranium ion is step number 2. This benzene ring nucleophile is ready to attack the NO2+. It used the double bond, 2 electrons here, used to form bond with the nitrogen. So one of the carbon will be bonded to NO2, another carbon will be positively charged. So if this carbon is bonded to NO2, the carbon on top here will be positively charged. It doesn't matter which carbon will be bonded to NO2 as long as one of any of these two carbon. So means another carbon will be positively charged. So this carbon is positively charged, will be stabilized by this double bond. This double bond will move its position to here to stabilize this carbon, and then making this carbon becomes positively charged. So the double bond over here move its position to stabilize this carbon, but making this carbon positively charged. So this is what we call as aromatic ion. And then step number 3 is loss of proton in the form of H+. So since this carbon is positively charged, the HSO4 form bond with the hydrogen over here, and this bonding electron, two electrons bonding used to form double bond in the aromatic ion, making stable aromatic ring again with a substituent of NO2, and this HSO4- become H2SO4 again, and this can be used in step 1 again. Next, FRIEDEL-CRAFTS alkylation. Reactants are benzene and alkyl halide. Condition: catalyst Lewis acid such as ALCl3, FeCl3, FeBr3, and etc. So benzene as a reactant, alkyl halide as the second reactant. So R group can be any alkyl group, X must be halogen atom. For example, these benzene rings react with this alkyl halide chlorine attached to alkyl group in the presence of catalyst AlCl3. The product will be, you just remove this Cl and attach that carbon to the benzene ring. The carbon that will attach to the benzene ring is the carbon that is attached to the halogen, not other carbon. Whichever carbon that attached to the halogen initially, that carbon will be attached to the benzene ring in the product. And the side product is HCl. This is FRIEDEL-CRAFTS alkylation, means you attach alkyl group to the aromatic ring in the presence of catalyst Lewis acid. Mechanism of FRIEDEL-CRAFTS alkylation. Step number 1, formation of Lewis acid-base complex or carbocation. So we need to form Lewis acid-base complex or carbocation. Initially, we start with the alkyl halide reacts with the catalyst Lewis acid. Start with the halogen in alkyl halide, use 2 electrons lone pair to form bond with Al, because we know this Al has 3 bonds only, incomplete octet. Makes this Al as electrophilic site, the Cl nucleophilic site. So nucleophile attack electrophile, this nucleophilic site Cl, 2 lone pairs electron form bond with Al. And this is Lewis base complex. Okay. After this complex is formed, then the CCl bond, the alkyl group, and the halogen bond, this bond, 2 electrons from this bond will be transferred to the Cl, because Cl now is positively charged, because it lose 2 electrons here to form bond with the Al. So Cl positively charged, Al negatively charged. And the Cl prefer to have the lone pair again by taking these 2 bonding electron to itself, leaving carbocation and AlCl4-. The minus is at Al, not at Cl, it's at Al. because Al prefers stable incomplete octet, but now it is octet, so that's why Al is negatively charged, and this is carbocation. Step number 2, formation of aluminum ion. Now carbocation is electrophile. Now it is ready to be attacked by aromatic ring. This aromatic ring uses its double bond to attack the electrophile. Electrophilic site is carbocation, so it will use 2 electrons from the double bond to form bond with the carbocation carbon in the carbocation. So any of this carbon or this carbon can be bonded with this carbocation. If this carbon over here bonded to the carbocation, another carbon will become positively charged, and it will be stabilized by the double bond near to this positively charged. So this double bond change its position to make this carbon stable. Now this carbon stable, but new problem, this carbon become positively charged, and the near double bond will change its position to stabilize this carbon positively charged, making this carbon positively charged. These are the resonance structures, so it keeps moving. The position of the double bond keeps moving to stabilize the positively charged carbon. So this is what we call aluminum ion. Step number 3, we have the AlCl4 minus. The AlCl4 minus. So here, this Al, as I've said before, it does not prefer to be negatively charged. It is stable when it is incomplete octet. So it will give these 2 electrons, both 2 electrons will be transferred fully to the Cl. And then the Cl will use one of its lone pair to form bond with the hydrogen. And then, in order for this to form bond, it needs to break this bond. So these 2 electrons will be transferred to become the double bond over here. And you have the product, benzene ring attached to alkyl group, HCl, this HCl side product, and AlCl3 catalyst can be used again in step number 1. Next, reaction FRIEDEL-CRAFTS acylation, benzene and acid chloride. So FRIEDEL-CRAFTS acylation is exactly the same like alkylation. The only difference is it is acetyl chloride. In alkylation, alkyl group with halogen. Now C double bond O with halogen. That's the only difference, acylation and alkylation. The product will be ketone, and the catalyst is the same, Lewis acid catalyst, same as alkylation. Okay, the only difference is acyl group is used. The mechanism of FRIEDEL-CRAFTS acylation, step number 1, formation of acylium ion. Acylium ion, first one is this AlCl3 Lewis acid catalyst will be used to react with this acyl chloride. As I've mentioned before, this AlCl3 is incomplete octet. The Al has 3 bonds only, so that's what it makes Al as electrophilic site. This Cl nucleophilic site. This Cl will use 2 electrons of its lone pair to form bond with Al, forming this complex ion. And then the Cl prefers to be negatively charged, but now it's positively charged, so it used 2 of the bonding electron between C and Cl, both 2 electrons transferred to itself, making this acylium ion C positively charged, and it can also be written as C triple bond O plus, because when this carbon is positively charged, this oxygen here, oxygen rich in electron, because it has 2 lone pairs, so it will use one of its lone pair, both electrons here, to form one more bond. It will become triple bond. When the oxygen is positively charged, because it loses two electrons lone pair, that's why this oxygen positively charged. So this is resonance structure of a helium ion, can be like this or like this. And this AlCl4 minus, because these two electrons transferred fully to the Cl atom, so it becomes AlCl4 minus. The minus is at Al atom, because this Al now has 8 electrons in total. Step number 2, the helium ion now is ready to be attacked by the aromatic ring. So it attacks at the carbon positively charged. The double bond of the benzene ring, the electrons of the double bond will be used to form bond with the carbon positively charged in helium ion to form aranium ion over here. So one of the carbon form bond with this carbon, another carbon will become positively charged, stabilized by the double bond in the ring. These are aranium ion. And then step number 3, loss of H+. Since we have AlCl4 minus, this Al does not prefer to be minus, so it will transfer this sharing electron, 2 electron transferred fully to the Cl, and this Cl will use its lone pair to form bond with the hydrogen in the aranium ion. So form bond with this hydrogen, and this bonding electron will be transferred to the carbon positively charged in the ring to make it aromatic ring again, stable aromatic ring again, with the product here C11O alkyl group plus HCl as the side product, and the AlCl3 catalyst can be used again in step number 1.